My dear students, let me welcome you all to a new edition of physics. In this edition, we'll revise chapter 2. We'll revise the electrical instruments. So we'll be encountered by miscellaneous questions. Questions such as write the scientific term, write the scientific expression that expresses, define, and we'll try to solve some problems. So let's get started. Revision on electrical instruments. The first question is we want you to write the mathematical relation that expresses. We want you to write down the relation that expresses Ampere's circuit law. Okay, it's all easy for you. What about the relation that expresses Ampere's circuit law? Yes, beta equals mu I over 2 by d. Let me say it again. Beta equals mu I over 2 pi d. This is the relation we usually use to determine the magnetic flux density at a point of normal distance d from, yes, current carrying a straight wire. So Ampere's circuit law, the expression that expresses it is beta equals mu I over 2 pi d. And what about the relation that expresses the law of conservation of energy? Okay, law of conservation of energy is the first law of Kirchhoff voltage law. Law of conservation of energy is the second law of Kirchhoff. It is the Kirchhoff voltage law. It states the algebraic sum of all voltages encountered in any loop equals 0. The algebraic sum of all voltages encountered in any loop equals 0. Summation of voltage equals 0. And what about the relation that expresses the law of conservation of a charge? Law of conservation of a charge is the first law of Kirchhoff. It states that the sum of the currents arriving at any junction point at any node in a circuit must equal the sum of the currents leaving that point. The expression we usually use, summation of current equals 0. Also we can say the algebraic sum of the currents flowing into and out of a junction is 0. Once again, summation of current equals 0. And what about the relation that expresses Ohm's closed circuit law? Ohm's law for a closed circuit. Okay, it's all easy for you. The current passing through the circuit, current through the battery, I, equals V battery over R capital plus R small. So once again, current through the battery equals VB over R capital plus R small, R total of the circuit. This is the expression that gives Ohm's law of a closed circuit. And what about the expression that gives the quantity of electricity that passes through a conductor in 1 second? The quantity of electricity that passes through a conductor in 1 second. We want the expression that gives the rate of flow of electricity. Yes, thank you very much. Current intensity equals Q over T. Current intensity is the quantity of electricity that passes through a conductor in 1 second. And what about the relation that gives the intensity of the electric current when the rate of flow of electricity is coulomb per second? Intensity of the electric current when the rate of flow of electricity is coulomb per second. Intensity should be ampere when the rate of flow of electricity is coulomb per second. So we want the relation that gives ampere in terms of coulomb and second. Of course, it's all easy for you. Since I is equal to Q over T, so ampere equals coulomb over second. And what about the expression that gives the quantity of electricity? We want the quantity of electricity which passes any point in a circuit in 1 second when a steady current of 1 ampere is flowing. Yes, of course, I can hear you saying it is coulomb. Since Q is equal to I times T, so coulomb is equal to ampere times second. And finally, what about the relation that gives the scale deflection per unit current intensity flowing in the coil of the galvanometer? So we want an expression that expresses the scale deflection per unit current intensity, and unit current intensity here actually is 1 microampere flowing in the coil of the galvanometer. Of course, we want a relation that gives the sensitivity of the galvanometer. Sensitivity of the galvanometer is given by the expression S is equal to theta over I. Another type of questions define. We want you to define the electric current intensity, and it's all easy for you. It is just a recalling. What about the electric current intensity? It is the quantity of electricity that passes through a conductor in 1 second. And what about the potential difference between 2 points in a circuit? So define potential difference denoted by V between 2 points in a circuit. Yes, it is the work required to transfer unity charge, to transfer 1 coulomb between these 2 points. And what about the definition of volt? Volt is the unit of potential difference. So it is the potential difference between 2 points when a work of 1 joule is required to transfer 1 coulomb between these 2 points. Let me say it again. We want you to define volt. What about volt? It is the potential difference between 2 points when a work of 1 joule is required to transfer 1 coulomb between these 2 points. Something similar to potential difference, which is electromotive force or V battery. We want you to define electromotive force of a cell. What about the definition of the electromotive force of a cell? Yes, it is the work required to transfer unity charge. Once again, unity charge means 1 coulomb through the whole circuit, throughout the whole circuit. That's to say, through the external circuit as well as the internal circuit. The work required to transfer 1 coulomb through the external circuit, we call it, yes, terminal voltage. And through the battery itself, you call it, yes, internal voltage or lost voltage. And there is something very important. There is another definition of electromotive force of a cell. Electromotive force of a cell is its terminal voltage when no current passes, when no current flows. Okay? And what about the definition of electric power? Okay, power is given from the expression energy over time. So it is the rate at which the electric energy is converted, rate of conversion of electric energy. It is the electric energy converted, consumed or produced in 1 second. It is the power. And what about the definition of watt? What is the power of the device? It is the power of the device which dissipates electric energy at a rate of 1 joule per second. Let me say it again. What about the definition of watt? It is the power of the device which dissipates electric energy at the rate of, yes, joule per second. And what about ohm? Definition of ohm. Ohm is the unit of, yes, electric resistance. It is the resistance of a conductor. It is the resistance of a conductor which passes a current of 1 ampere, when the potential difference applied across the ends of the conductor is 1 volt. Once again, definition of ohm. It is the resistance of a conductor which passes a current of 1 ampere when the potential difference applied across the ends of the conductor is 1 volt. And definition of resistivity of a material at a given temperature. You know, resistivity depends on kind of material and temperature. We want you to define resistivity of a material at a given temperature. Yes, actually it is the resistance of a wire made of that material. The wire should be 1 meter in length and 1 meter squared in cross-sectional area at that stated temperature. This was about the definition of resistivity. And what about the definition of magnetic flux density? Magnetic flux density at a point. Magnetic flux density is denoted by beta or B. It is equal to phi over A. So it is numerically equal to the number of flux lines passing normally through unit area at that point. It is numerically equal to the number of flux lines passing normally through unit area at that point. And we want you to define Tesla. What about Tesla? Tesla is the magnetic flux density of the uniform field which exerts a force of 1 Newton on a wire 1 meter in length, carrying a current of 1 ampere and placed at right angles to the field. So definition of Tesla is the magnetic flux density of the uniform field which exerts a force of 1 Newton on a wire 1 meter in length, carrying a current of 1 ampere and placed at right angles to the field. And finally, definition of magnetic dipole moment of a coil. Yes, this is a little bit difficult. It is the torque exerted on the coil when placed with its plane parallel to a magnetic field of density 1 Tesla. Let me say it again. It is the torque exerted on the coil, okay, when placed, so the coil should be placed with its plane parallel to the field, placed in the horizontal position. The torque exerted by, yes, magnetic field of density 1 Tesla. Another type of questions: when does each of the following quantities equal 0? Yes, we want you to tell when the quantity, mentioned quantity, will be equal to 0. When does the torque acting on a coil carrying an electric current and placed in a uniform magnetic field, yes, equals 0? Yes, this is very important. The torque equals 0 in the vertical position. It happens in the vertical position where the plane of the coil is perpendicular to the field. Okay, by the way, the torque is expressed by the relation. Torque is given by B, I, A, and cosine theta. B is the magnetic flux density, I current intensity, A is the face area of the coil, and number of turns on the coil. Cosine theta, theta is the angle between plane of the coil and the magnetic field. When theta equals 90, the torque will be 0, because cosine 90 is 0. Okay, when does the magnetic flux at any point inside and along the axis of a current carrying solenoid equal 0? Okay, this happens when the solenoid is made of a doubly wound wire. When the solenoid is made of a doubly wound wire, the field inside the solenoid is 0. Okay, when does the EMF induced in a wire moving in a uniform magnetic field equal 0? Okay, so we've got a wire and the wire is moved in a uniform field, but no EMF is induced. So the wire is moved parallel to the field. It happens when the wire is moved parallel to the field. Since EMF instantaneous is given from the expression BLV sine theta, B magnetic flux density, L is the length of the wire, V is the linear velocity, theta is the angle between direction of motion of the wire and field. So EMF instantaneous equals 0 when theta is 0, because sine 0 equals 0. Okay, so the wire must be moved parallel to the field. And by the way, theta is the angle between the field and direction of motion of the wire. When does the force of a magnetic field on a current carrying wire is 0? Force. So let me explain the question. We've got a wire, straight wire, and it is current carrying, and it is placed in a magnetic field, but no force acts on it. It happens also when the wire is placed parallel to the field. Force is determined from the expression BIL sine theta. Force equals 0 when theta equals 0. Another item, when does the difference between EMF of a cell and its terminal voltage, yes, equals 0. Actually, it asks you about the condition when the EMF of a cell is equal to its terminal voltage. Yes, it happens when the circuit of the cell is open. That's to say, the resistance across the terminals of the cell is infinite. Infinite means no current passes through the cell, okay, because the huge resistance, then EMF of the cell is equal to its terminal voltage. Also, theoretically, it happens when the internal resistance of the cell is equal to 0. Another item of the same question, when does the magnetic flux density at the midpoint between two current carrying parallel straight wires, yes, equals 0? Okay, it happens when the two wires carry equal currents in the same direction. So they should carry equal currents in the same direction. Another type of questions, give reason for. First, give reason. The resistivity of a material is regarded as a physical property, but its resistance is not. Resistivity of a material is a physical property, but we cannot consider resistance as a physical property. Simply because the resistivity of a material, unlike resistance, is a constant at any given temperature and is independent of the dimensions of the wire. Dimensions of the wire means length and cross-section area of the wire. Okay? But resistance depends on length and area. Another give reason, electrical conductivity of a pure metal is high. Electrical conductivity of a pure metal is high. Why? Because there are many free electrons that are not bound to any particular atom within the material. So the reason behind the conductivity is so high of conductivity of a metal simply because there are many free electrons that are not bound to any particular atom within the material. Give reason 4. The internal resistance of the emitter should be so low. Why? We want the emitter to have very low resistance. Okay, the resistance of the emitter should be so low so that it has no noticeable effect on the current in the circuit. Okay, and another give reason, the resistance of the voltmeter should be very high. Okay, if the resistance of the voltmeter were low, if it was low, a large fraction of the current flowing in the circuit would flow through the voltmeter, and the current flowing in the circuit is dramatically changed, is noticeably altered. Another give reason, the voltmeter is connected in parallel in electrical circuits. It asks why it should be connected in parallel. Okay, in this way, when it is connected in parallel, the voltage across the voltmeter is equal to the voltage across the element required to be measured, required to measure its potential difference. So we can take the voltage of the voltmeter and the voltage across the element we want to know the potential difference across its ends. Give reason 4. A work is required when transferring a charge between 2 points on an electric circuit. We need a work is required when transferring a charge between 2 points on an electric circuit. Why? To overcome the electric resistance between these 2 points. Another give reason, electric current is sent into 2 long parallel wires, but no neutral point can be detected. Let me say it again. Electric current is sent into 2 long parallel straight wires, but no neutral point can be detected. This happens when the wires carry currents of the same intensity in opposite directions. Another give reason, the moving coil galvanometer cannot be used for measuring alternating currents. This is very important give reason. The frequency of the alternating current is much greater than the frequency at which the coil can oscillate because of its inertia. Consequently, the galvanometer just records the average value of the alternating current, which is 0. Another give reason, the moving coil galvanometer is provided with hair springs, hair coils. As a matter of fact, it asks for the function of the spiral springs found in the moving coil galvanometer. Yes, hair springs carry the current to and from the coil. They produce a mechanical couple which opposes the rotation of the coil. That's to say, it counterbalances the electromagnetic couple. Hair springs return the coil to its initial position, to its 0 position when the circuit is broken, when disconnecting the galvanometer. Okay. Another important give reason, the scale of the moving coil galvanometer is uniform, is linear. It is equally spaced. Yes, this is because the poles of the permanent magnet are curved to make the flux lines radial to the core. In other words, the magnetic flux becomes uniform and is parallel to the plane of the coil, perpendicular to the sides of the coil, and parallel to the plane over the region in which the coil can swing. Consequently, the angle of deflection of the coil, theta, is proportional to the current, and the scale is then uniform. Give reason, the coil of the galvanometer is connected to a low resistance in parallel. Yes, coil of the galvanometer is connected to a low resistance called shunt when we want to convert it into a meter. Why we want to convert it into a meter? To measure higher current intensity. So the coil of the galvanometer is connected to a very low resistance in parallel to convert it into a DC ammeter. And let me remind you with the functions of the shunt. It extends the range of the device. The shunt increases the range of the device. It decreases the total resistance, the internal resistance of the device, thus decreasing the heat produced in the device. And as a matter of fact, most of the current entering the device flows through the shunt, and only a small fraction of the current passes through the galvanometer, so the device is not ruined. Another give reason, the coil of the galvanometer is connected to a high resistance in series when converting it into a DC voltmeter. Yes, this high resistance connected in series to the coil of the galvanometer is called multiplier. We want the function of the multiplier. First of all, it extends the range of the device. It increases the total resistance of the device, thus decreasing the heat developed in the device during its operation. And another give reason, the coil of the galvanometer is connected to a standard resistance when converting it into an ohm meter. Okay, so we want the function of the standard resistance, Rs. Without the existence of the standard resistance, Rs, the current flowing in the circuit of the ohm meter would be too excessive, and it would simply heat the coil of the galvanometer and burn it out. Another give reason, the internal circuit of the ohm meter contains a variable resistance. Okay, each time the ohm meter is used, what happens? It is first short-circuited, and the variable resistance is adjusted to zero the device, to zero the meter. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.